Our next two speakers begin a track alongside the meetup group Sussex Data Science, with both talks today incredibly relevant to the current COVID-19 situation. A graduate from the Universities of Oxford and Leeds, and now Professor of Applied Mathematics at our very own University of Sussex, Istvan Kiss will today explain how mathematical models of infectious disease spread work. You do not need to be technical for this talk. Istvan explains these models in a way we can all understand.
Hello, thank you for joining me. My name is Istvan Kiss and I am a professor of applied mathematics at University of Sussex, and today I'm going to talk to you about how do mathematical models of infectious disease spread work. So let me start with some simple facts. Obviously, the process of infectious disease transmission in a real population is quite a complicated one, so therefore probably every model is simply going to be just a caricature of the real life process, and this is obviously translated in mathematical language. And as the famous statistician George Box said, all models are wrong, but some are useful. And obviously the quality of a model is basically given by the assumptions that have been used to build that model. So obviously if our assumptions are more realistic and closer to what we observe in real life, then the model is gonna become more relevant. So assuming that we have built a competent model that takes into account all the major mechanisms, then the great advantage of that model is that relatively cheaply we can explore lots of different control scenarios, different what-if scenarios, and we can use that model to make forecasts and predictions. We can inform even policy making and so on. So developing good models potentially has extremely positive benefits. So before we move on to how a model is built, let me talk to you a little bit about the main trends and the overall pattern in an epidemic. And these are universal in the sense that it doesn't matter if we look at different diseases in different populations, then an epidemic is going to have the same overall trends. First of all, the epidemics are stochastic. So this basically means that if COVID-19 happens again, then if you look at the number of cases, the number of counts, they are going to be slightly different. The timescale might be similar, but we are going to notice a slightly different pattern. However, what's universal between all these epidemics is the fact that the epidemic starts with an initial phase where the epidemic is trying to become established. Then this is followed by a growth phase where the epidemic is happily spreading along and infecting lots of people. Then obviously there is a peak time of the epidemic followed by a tail, where unfortunately it's possible to have little mini epidemics, little resurgence of the epidemic in the wake of the epidemic actually going extinct. And here on the right hand side, I'm simply plotting some of the data from the government's website on the total number of lab confirmed cases in England and also the total number of associated deaths in the UK. So quite serious and sobering numbers. Okay, so let me talk a little bit about the branching process in main detail. So this is a kind of first modeling attempt, and this is only going to be valid at the beginning of the epidemic. And actually this model has only one ingredient, only one parameter, and this is R0, the basic reproduction number, which in layman's term means that this number is the average number of new infections caused by a single infected individual during its lifetime when introduced into a fully susceptible population. So basically this means that if I'm becoming infected and I'm going to be infectious for 5 days, then how many new infections I'm going to generate before I become susceptible again or removed. So a simple example here is that we are assuming that R0 is 3, so the initial infected individual leads to 3 new cases, and then each of these 3 on its own leads to 3 more cases. So as you can see, the numbers are growing exponentially, so we have one index case and then we go on to 3, 9, 27, 81, and by the 9th generation, so imagine a chain of transmission of length 9, then we are in the tens of thousands. Now, obviously, the assumptions of this model is rather strong. Basically, here we are assuming that the epidemic just goes on, and we know that's not the case. Governments, individual, organization react to the presence of the epidemic, and immediately the contact structure in the population changes. Obviously, now we are in the middle of a lockdown, so simply infectious individuals are going to be starved of new susceptible cases, and exactly that's the point. We are aiming to get this number, this basically production number, below 1, since this will mean that on average an infection individual produces less than one infectious individual, meaning that the epidemic eventually is going to die out, and this is the scenario that everybody is trying to be in. Okay, so as I said, this is a rather crude assumption, and it does work in the beginning of the epidemic, but if we want to build a more realistic model, then we have to think about the biology of the disease. And one of the simplest but most widespread models is the so-called susceptible, infected, recovered model, where basically we are just dividing the population into 3 different compartments. So imagine that you have a compartment where you have all those guys who are susceptible, and then another compartment where you have the infected people, and then finally a compartment where you have the R, the recovered or dead people, and then you need to just model the flow. How do people move from susceptibles to being infected, and then from infected to being recovered? And in order to be able to write down such a model, a very important consideration from the biology point of view is actually how does disease transmit. And obviously, for infectious diseases, the most important component is the contact. How do individuals come into contact? So one can think that we need to model at least some kind of contact rate. So for example, what is the average number of contact that people or a typical individual makes per day? But then we also need to model the transmission, the possibility that a contact between a susceptible and an infected individual actually is going to transmit the infection, and this is denoted by P. So this leads to the so-called disease-specific transmission rate, which is the product of the two. So the rate at which I'm making contacts times the probability, this is a number between 0 and 1, then such a contact is going to result in a new infection. Now here I have a little caricature. So this looks like a big vessel, a big urn, where you have individuals, and basically I'm just mixing them around. So basically I'm making the assumption that individuals freely can come into contact with any other member of the population. And this is like a very strong underlying assumption of many simple models. And obviously this is a first approximation, but in real life, the way how individuals contact each other is much more complicated. So it doesn't happen homogeneously at random. So we are not just mixing randomly like gases in physics. So as I was saying on the previous slide, individuals do not move around as particles in gases, but rather the contact structure is much more complicated. And let us explain in a little bit more detail how the susceptible, infected, recovered model works. So we have individuals separated into different classes based on their disease status. So we have the groups of those who are susceptible. These then at certain rates are gonna move to the infected and infectious class. And then again, after a certain time, when the infection is cleared or indeed the individual is removed or dead, then obviously we move to the recovered class, and individuals play no further role in the epidemic. So in terms of the mathematical model, this translates into a system of so-called ordinary differential equations, where, for example, the rate of change in the number of susceptible obviously is going to be negative, meaning that the number of susceptible decreases, and this is proportional first of all to beta I. So these are the number of contacts, infection transmitting contacts made by I infectious individual, and they make contacts at rate beta. And then the model needs to account for the fact that not all of these contacts are going to happen with susceptibles. So these contacts can happen with other infected or other recovered individuals. And therefore we multiply by this S over N term, where N is the total population size, and this is always a number which is less than 1. And we can see that as the number of susceptible is depleted, then this quantity S over N, it becomes less and less than 1. So we also have an R0, a basic reproduction number, in this system of equation, and this is simply beta over gamma. And the interpretation of this is simply that an infectious individual on average is gonna be infectious for 1 over gamma, and then within that time window 1 over gamma is gonna make beta times 1 over gamma infectious contacts, and this really only applies at the very beginning of the epidemic. And again, if R0 is less than 1, then this is the fortunate situation where we are not gonna have an epidemic. However, if R0 is greater than 1, then an epidemic will happen. So let us see what this mathematical model tells us if we simulate it. So as you can see, the red curve is the epidemic curve. So we had an initial increase, a peak, and then the epidemic basically is becoming less and less potent, and the number of eyes goes to 0. In the meantime, the number of eyes, the number of susceptibles decreases, and the black curve basically just cumulates or counts all those individuals that have been through the infected class, and you can see that for an R0 of 2.5, the epidemic actually is quite severe and is about 0.9% of the individuals are going to become infected by the end of the epidemic. So once again, we have introduced a little more reality in the model. So we are more closely matched with the biology. So we have the susceptibles, infected and recovered, and then we have a few more parameters, the transmission rate and the rate of recovery. Okay, so let us just think a little bit about these two models. So on one hand, we had the branching process, which here is illustrated by this red line. So this is an ever increasing curve. So we have the same, in this situation, tripling potential. So every so often, the number of individuals is just gonna increase threefold every time. And funnily enough, the two models, so the differential equation model and this branching process, they agree pretty well for some time, but obviously, as I said before, the branching process does not account for the depletion of susceptible, and therefore really we are departing from the differential equation model and from what we see in the general epidemic curves. So this is already immediately to illustrate the fact that if we are making the model a little bit more accurate and we are trying to capture more of the important features of the disease, then the model is bound to get better. So for example, the branching process only depends on R0, so it depends on one single parameter, while the differential equation depends on the number of individuals in the population, the contact rate, beta and gamma, which perhaps I didn't cover in detail enough, but gamma is to do with how quickly an infectious guy is gonna move out of the eye compartment. Obviously, the longer you stay in that compartment, the more infectious you can make. And obviously, if we isolate people very quickly, very early on, then basically that amounts to a very high gamma, meaning that we are removing infectious individuals from that class very quickly. And therefore, if they spend lesser time in the environment, in the population, then they have less an opportunity to infect. So once again, the takeaway message: branching process, very simple, only works initially, but obviously it misses the real features of the epidemic. there is no peak and there is no tail in the epidemic, and it doesn't take into account the depletion of susceptibles. Okay, but what further complications can we talk about? Well, unfortunately, the complications are really very many, because real populations are not simply made up of completely equivalent individuals, but one important factor is obviously the age structure of the population. So just to make it simple, we can talk about young people, middle-aged, and old people. But obviously, this division can be made much finer. Here in this graph, you can see them that we group individuals by 0 to 4, 5 to 8, and so on. So we have quite a large number of different age groups. And actually, as it turns out, the way how these individuals interact, not surprisingly, it is very different. And these mixing matrices basically tells us and give us an idea how this different age group mix. So for example, you expect that children mix with children quite a lot, or there is also some mixing between children and their grandparents and so on. So this is an extremely important level of complication. And on top of it, then we have obviously people do live in household structures, if you like. Obviously there is a strong contact dynamics going on at workplace, and how people travel to schools and to workplaces and so on. And more importantly, there is geographical location, and usually the biology of the disease is much more complicated than the simple SIR epidemic. So basically what I'm trying to hint now is that we had the branching process, which was extremely simple, then we improved it by the differential equation model. But what I'm trying to suggest here, that actually the complication is indeed huge, because if we want to reflect the true population contact structure, then we have to think about all these factors: age structure of the population, and then more importantly, how do we measure the mixing, how much one age group mixes with another age group, and so on. And for this we need lots of surveys and very strong information. Otherwise our model is gonna become irrelevant. We can go on and we can talk also about the biology of the disease. Obviously, for example, for the COVID, we know that it's not as simple as an SIR. So probably it's more like we have a susceptible individuals, and obviously the susceptible individuals then become exposed and not yet potentially infectious, or they could be even infectious, so they could be asymptomatic and non-infectious, but asymptomatic and infectious. So the possibilities are endless. So for example, here, these are the people who go on to be asymptomatic and infected, and then they recover without ever going to the hospital. Or you have individuals who then go on to develop symptoms and they end up in the hospital, and then they are going to spend some time in the hospital, but eventually they manage to recover. And the more serious cases, they go on to into the hospital, but they are going to go on to need intensive care, and then they undergo the most serious treatment, and then there are two outcomes. This is the more positive one, which they recover, or this is basically being a victim of COVID-19. So you can imagine that this is a much more sophisticated model than the SIR model that I showed you before. But as you can see, the number of parameters increases hugely. Before we had the transmission rate and the recovery and the population size, and now all these symbols, all these letters that you see on the arrows, all these symbols, we need to have numerical quantities for this. So we need to have concrete numbers which can either be measured from trials or can be inferred from various studies. So now if we are going to write down a system of equations, then sometimes we can have in excess of hundreds of equations that we need to solve. And actually solving these equations is not complicated, but rather finding all these various parameters is. Now, one other important case that the differential equation make a very important assumption, namely that periods that infectious individuals remain infected for an exponential amount of time. So basically this means that every Most individuals recover very quickly, and some remain infectious for a longer period of time. And again, this is not very realistic. And for this, you need again to you need to input extra equation. You need to increase the number of equation in order for your model to become more realistic. So overall, if we want to increase the accuracy of the model, then we are going to pay the price into having more and more equations with more and more rates and parameters that we need to either infer or we need to get information about these. And obviously then the uncertainty and the sensitivity of the model becomes very important. Okay, so I myself did a little bit of work on COVID-19, but I was working with a simple SIR model because the complexity of the model is just overwhelming, and we have looked at the situation where we assumed that the government has the option of one-shot major intervention, so you can only intervene once with a drastic measure, and this drastic measure cannot be sustained in the long term, which is basically what we are facing now with the lockdown. And then the question that we asked is, if the government has this opportunity, when should they apply this policy? So let me just look at these graphs, and what we are showing here is the number of infected over time, and the dashed line is when there is no intervention. So this is quite a normal epidemic. So we have the growth phase, and then we have the peak of the epidemic, and then eventually the epidemic tails off. And here I'm showing two scenarios, two optimal scenarios from different points of view. So obviously this curve here, the cyan, basically what happens is that intervention happens early. So then when the intervention happens, then the number of eyes starts to go down, the epidemic decreases. But when the intervention is stopped, then unfortunately you still have plenty of susceptible people, and the epidemic will pick up again, and then we're going to have a second peak, which is quite a possibility. And of course that this is what people are afraid of, that if the lockdown is going to be lifted, then we might have a second or a third or maybe even a fourth wave. Now the other scenario, the green line, so what happens in the green line is that we let the epidemics spread for a little bit longer, and we intervene a little bit later. And in that situation, once the lockdown is lifted, then the epidemic cannot increase again, but is gonna tail off eventually. But obviously, the peak reducing strategy is quite important, because we all know that the NHS and the healthcare system have limited capability. So we rather deal with two small peaks rather than dealing with one large peak. So obviously this, again, it's a very simplistic model, and nevertheless the outcome of the model and the results make intuitive sense, and the overall finding as well kind of align well with all the discussion around controlling COVID around the world. Okay, so now I'm getting closer to an area which is very dear to me, and I worked on it a lot. And I would say that probably the most sophisticated model that we can think of is what is called an individual-based or a network model, where we would attempt to model each individual as a node in the network. So you can imagine that I am a node in a network, and then all my family and friends are represented by different nodes, and then we draw lines between ourselves to say that, for example, myself and my daughter and my wife are connected, and so I am connected with all my work colleagues and so on. And here on the left hand side, I'm showing a typical realistic picture of a school contact pattern. And as you can see, these nodes of different color represent school children in different classes, and then the links between them represent the way how they interact during a day. And then obviously the most of the contacts are going to be within a class, but you can also have some mixing between the classes. Of course, another important component in the whole story of infectious diseases is obviously global travel and the movement of people around the world, where obviously infections can be very easily imported via via air transportation networks. And obviously, indeed, even if a country right now clears COVID-19, it's very important that they are going to put very severe and very strict testing and contact tracing measures in place at airports, because obviously importation and reintroduction from countries who have not cleared COVID are indeed very high. So these risks indeed are very high. So therefore, very strict testing and contact tracing is needed, especially in the lower tail or towards the end of the epidemic. Now here another picture that I'm showing. This is the initial spread of the foot and mouth disease. So this is an animal disease of hoofed livestock, and this just shows how the movement of livestock has allowed to spread foot and mouth disease to different geographical locations and start little local hotspots. So we might ask, why are networks important? And in order to answer this question, I built two networks here. This is a simulation. Hopefully it's going to be quite illustrative. So on the left hand side, I have a simple lattice. So everybody has four immediate neighbors, up, down, left and right. Obviously those on the edge, they have fewer links. And on the right hand side, I have the same, but here you can see that there are occasional shortcuts in the network. And I just wanted to illustrate that putting in a few shortcuts in such a network is going to make a big difference, and I'm hoping that this is now going to work. So let's see. So the simulation started. This is an SIR epidemic. Initially, all the black nodes are susceptible. The red ones are the infected ones. And then the blue are the recovered ones. So you can see that the epidemic starts spreading like wildfire, and it goes in a very spatially localized way. But let me just I wanted to pause this, which right now I can't. Well, let me try now, maybe I can. So let me restart the video again. And the most important thing to note is that indeed, when we have these shortcuts in the network, then what happens is that the infection is receded. For example, here we have a new pocket of infection. We have a new pocket of infection here, and then basically this leads to a much faster epidemic. You can see the red curve rising here compared to this red curve. Having a few extra shortcuts in the network is going to make indeed a very big difference to how the epidemic spreads in the two situations. Thank you very much for your attention. I hope that this was informative. I am happy to answer any questions. I'm sure the organizers are going to make the details somehow available. But in the meantime, if you're interested, then please do look up the book, which I published not so long ago, and this was focusing on the mathematics of epidemics on networks. Thank you and stay safe. Bye bye.